Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or if you needed any help with tutoring, then check out the links in the description below. Now I'm just going to get started on my set of questions for today's session. All right. Question number 1 asks, what are valence electrons? So this is an example of like a high school chemistry question. But basically, valence electrons are the electrons that occupy the outermost shell. They're the electrons that would be taken first in a chemical reaction. I'm just going to have like an example just to draw out valence electrons. So let's say we have sodium. If you find sodium on the periodic table, it has an atomic number of 11. So this means that it has 11 protons. And when you have 11 protons, you need 11 electrons to make it a neutral atom. So I'm just also going to write down 11 electrons. So since we need 11 electrons, I'm going to draw out this diagram of sodium. So the first shell only contains 2. And then the shells after that will all contain 8. So we have 2, 3, 4, 5, 6, 7, 8, 9, 10. So we need one more. 11. So here I drew out 11 electrons for sodium. And if you look, it only has one valence electron. That's kind of like an easy way find out how many valence electrons you have. I'm just going to see what the junior tutor said. So valence electrons are the electrons that occupy the outermost or highest principal quantum number, n, level. For example, carbon with an electron configuration of 1s2, 2s2, 2p2 has n equals 2 as its highest principal quantum level. That means that it has 4 valence electrons in total. Consider this other example. Sc, I forget what element that is, but it has 21 electrons distributed as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. So this is an example of an element that has many electrons. Thus, it has 2 valence electrons found in the 4s orbital. This is because n equals 4 is the highest principal quantum level. So this is another method of how you would figure out how many valence electrons are in an atom. I'm just going to say this solution is correct since they gave the correct definition. Okay, so now we are moving on to question number 2. It's just a simple, how do you convert grams to moles? So grams is a unit of mass. And moles, it's just straightforward, it's just mole. And basically, to convert grams to moles, you would use the equation N equals mass over molar mass. So number of moles is equal to mass in grams divided by molar mass, and its units are in grams per mole. So the molar mass is found on the periodic table. And basically each element has a specific molar mass. When you have compounds that have different atoms in it, then you would take the sum of all of their molar masses with respect to how many atoms there are in each compound in order to calculate molar mass. So let's have just like a short example. So let's say I wanted to find how many moles in like 10 grams of oxygen. So there are 10 grams, and the molar mass of oxygen is 16 grams per mole. Therefore, you get 0.625 moles. And you know you did it right if the units cancel out in the way that you wanted to. So we want to get rid of our grams and have our moles as the main units. And you get 0.625. That's if you, this is just if you have like a single oxygen, not O2. We need, so I'm gonna read what our junior tutor said. Two important values to convert grams to moles: the molecular weight of the substance, or in the case of an individual element, its atomic weight, and also you need the number of grams. For example, we want to convert 10 grams of water to moles. First, we need to determine the molecular weight. We need the chemical formula to know how many atoms there are for each element. 2 atoms of hydrogen, 1 atom of oxygen, and then multiply the number of atoms with the corresponding atomic weights. So they get the molar mass of water to be 18.015 grams per mole. And now that we have determined the molecular weight of water, we can convert grams to moles. We divide the number of grams of water by the molecular weight. So they have 10 grams divided by 18.015 grams per mole. And they got 0.555 moles of water. So this solution is correct. Now let's move on to question number 3. How do you calculate formal charge? So first I'm just going to write down the definition of formal charge. And basically this is the charge associated to an atom in a molecule. So we can use the following equation. So formal charge is equal to the number of valence electrons in the atom minus, in square brackets, the number of non-bonding electrons plus the number of bonding electrons divided by 2. So this is because each bond contains 2 electrons, and if we want to find the formal charge of one of the atoms, we need to divide it by 2 to find out how many electrons are associated with that one atom. So I'm going to have an example here. I'm just going to draw out like a hydrogen that has 3 methyl groups and also a single bonded oxygen. And I want to find out the formal charge of all the atoms. So let's say nitrogen, oxygen, and also carbon. So let's do oxygen first. For oxygen, its formal charge is equal to the number of valence electrons in an oxygen atom. So for oxygen, that would be 6, minus the number of non-bonding electrons. So let's look at our oxygen atom right here, and you'll see that there are 1, 2, 3, 4, 5, 6 non-bonding electrons, or like valence electrons, plus the number of bonding electrons divided by 2. So there's a bond here that contains 2 electrons, so I'm going to write 2 divided by 2. So it's going to be 6 minus 6 plus 2 over 2. So that is 7. So 6 minus 7 is equal to minus 1. So for oxygen, there's a formal charge of minus 1, so I'm just going to write a negative charge beside the oxygen. So now let's do the same thing for nitrogen. Its formal charge is equal to nitrogen's valence electrons, which is 5, minus the non-bonding electrons. So you see that this nitrogen has no lone pairs, so I'm going to write 0, plus the number of bonding electrons divided by 2. So that you can see that there are 4 bonds attached to nitrogen, and each bond contains 2 electrons, so therefore there are 8 bonding electrons divided by 2. So this is saying the same thing as 5 minus 4, which is plus 1. So now I'm going to write a plus charge on my nitrogen atom. And then lastly, let's also look at the formal charge of carbon. So the number of valence electrons in a carbon atom is 4. So we can just look at the one carbon atom. You'll see that there are no valence electrons. No lone pairs of electrons. So I'm gonna write 0. And each carbon has 4 bonds attached to it. So that's because there are 3 hydrogens. And then each one has a single bond to nitrogen. So again, I'm just going to do 8 over 2. So this is the same thing as saying 4 minus 4. So each carbon has a formal charge of 0. So we can also double check and see if this makes sense. Nitrogen has a +1 charge and oxygen has a -1 charge. So the entire molecule is neutral. So let's see the answer from our junior tutor. The formal charge of an atom is the charge assigned to an atom in a molecule, assuming that electrons are shared equally between two bonding atoms, regardless of relative electronegativity. So determining the formal charge of each atom in a molecule is important in order to determine the electron distribution in a molecule. Combining all the formal charges of atoms will also result in the overall charge of the molecule. Moreover, in determining the Lewis structure of a molecule, the structure with the most formal charges of 0 on atoms is the more stable structure. In calculating the formal charge, we use the equation below. Fc equals valence minus non-bonding electrons minus bonding electrons divided by 2. So here they have an example with the nitrate ion, and they drew out its corresponding Lewis structure. So first they calculated the charge of the central nitrogen. Nitrogen belongs in group 15, has 5 valence electrons on its outermost shell. Because there are no lone pairs attached to N, the non-bonding electron is 0. So that's the same as my example as well. But lastly, since there are 2 single bonds and 1 double bond attached to it, the number of bonding electrons are 8. Calculating for the formal charge of nitrogen, we have +1. And then they also calculated the formal charges of each individual oxygen atom. So they first looked at the top oxygen, has a valence number of electrons of 6. There are 6 electrons in the lone pairs. There's 1 bond with 2 electrons, so they got -1. If you look at the leftmost oxygen, it also has a -1 charge. But if you look at the oxygen on the right that has the double bond, it has only 4 electrons participating in the lone pairs, and it has a double bond, so there are 4 electrons involved, divided by 2, and this formal charge of the oxygen on the right will only equal to 0. So then they took the sum of all of the formal charges that they got, so +1, -1, -1, and if you add it all up, you get a resulting charge of -1 for the entire molecule. So this corresponds to the overall formal charge of the nitrate ion. That was a good example and explanation, so this solution is correct. So now let's move on to question number 4. What is the molar mass of hydrochloric acid, also known as HCl? So when we want to calculate the molar mass, we first want to look at the different atoms involved in hydrochloric acid, and we want to find out the atomic weight of each of those atoms. So I'm going to write down the molar mass of hydrogen. It's 1.01 grams per mole. And let's look at the molar mass of chlorine. It's 35.45 grams per mole. So these are values that you would find on your periodic table. And if you want to find the total mass of hydrogen of hydrochloric acid, it's just going to be the sum of those values. So it's going to be 1.01 grams per mole plus 35.45 grams per mole. And then you get total molar mass value of 36.46 grams per mole. So let's see what our junior tutor said. Molar mass is the weight of a substance measured in how many grams there are per mole of a substance. We can get the molar mass by adding the atomic mass of all the elements in a compound. The atomic masses of elements can be found on the periodic table. Hydrochloric acid, the elements we have in the compound are hydrogen and chlorine. And then they wrote it down below. Adding the masses together, we get the molar mass of HCl, which is 36.46. This solution is correct. So question number 5 asks, how many moles are there in 28 grams of carbon dioxide? So first we can find, first let's use the equation. Number of moles is equal to mass over molar mass. We know the mass is 28 grams. And now let's calculate the molar mass of CO2. So the molar mass of CO2 is going to be equal to the molar mass of carbon plus the molar mass of oxygen times 2. So again, these are values that you would find on your periodic table. So the molar mass of carbon is 12.01 grams per mole. The atomic weight of oxygen is 16.00 grams per mole. And we are going to multiply this value by 2 since there are 2 oxygens in carbon dioxide. So if we were to add these values up, you get a molar mass of 44.00 grams per mole for carbon dioxide. So the question is asking how many moles there are. So let's use this equation up here. We have 28 grams divided by 44.00 grams per mole. And you end up with a number of moles of 0.636 moles of CO2. So again, if you get confused about which one is on top, like mass or molar mass, always pay attention to the units. So you'll see our grams should cancel out and our moles should go from the denominator to the numerator. So let's see what our junior tutor said. To calculate the number of moles using the given mass of a compound, we will use the equation below. Number of moles is equal to mass over molar mass. They then calculated the molar mass of CO2, and then they did 28 divided by 44 and got 0.636 moles. So this solution is correct. So now let's move on to question number 6. How many milliliters are there in 1 liter? So I'll just quickly write out that in 1 liter, there are 1,000 milliliters. So it's just a simple conversion question. So let's see what our junior tutor said. Converting from one unit to another unit in the metric system involves multiplying or dividing factors of 10. Milliliters has the prefix milli, which in the metric system means a factor of 1,000th. So for milliliters to liters, we divide milliliter by 1,000 to get the same volume in liters, or multiply it by a conversion factor of 1 over 1,000. For example, 500 milliliters in liters would be, and then they have 500 mils times 1 over 1,000 gets 0.500 liters. This solution is correct. Okay, so now we'll check out question number 7. How do you calculate for the percent yield? So I'm going to write down the equation for percent yield. I before E. And basically, this is your actual yield. And by actual yield, I mean like the mass that you obtain in your actual experiment. So your actual yield will be divided by your theoretical yield. And then this value is multiplied by 100% to convert to percentage. So theoretical yield is the value that you obtain when you use stoichiometry. And your mass of reactants. To calculate how much product you expect to have. So in an ideal world, if you do an experiment and you want to calculate a certain amount of water, we should be able to calculate how much we expect to produce, and it should ideally be the same as our actual yield. But most of the times this isn't the case. Like sometimes you get less than what you expect, so that's why we need to calculate percent yield to see how accurate we were in doing the experiment. So there are other times where you get more than you need to, and that's when you know you might have done something wrong. If you get a percent yield that's like above 100%. So let's see what our junior tutor said. They said to calculate for the percent yield, we need to first calculate for the theoretical yield. Calculate for this, we use stoichiometry. So here they give a nice example of silver nitrate and sodium chloride to yield silver chloride and sodium nitrate. And then this is given by the chemical equation. So everything reacts at a 1-to-1 ratio. If we used 15 grams of silver nitrate, theoretically we will obtain, and then they calculate it out. So to calculate the theoretical grams of silver chloride, let's say, you have your 15 grams of silver nitrate, and then you want to find out the number of moles that you get for silver nitrate. So they did that just by dividing by the molar mass. And then to convert how many moles of silver chloride, you need to multiply by the molar ratio. So they did 1/1. And then to find the mass you would theoretically obtain, you need to multiply those moles by the molar mass of silver chloride. So theoretically, if we used 15 grams of silver nitrate, you should get 12.65 grams of silver chloride. If the actual yield is 9.7 grams of silver chloride, the percent yield can be calculated using this formula. So percent yield is equal to 100% times actual over theoretical yield. So you do 9.7 divided by the theoretical 12.65 times 100. So here their percent yield was 76.646%. So that's actually pretty good. So this solution is correct. So they gave a good example of how you would calculate a theoretical value. So that's why it's always important to make sure that your chemical equation is balanced. So let's say everything wasn't in a 1-to-1 ratio, then your molar ratio would be like a different value. So just make sure you know how to do that as well. Okay, so now let's move on to question number 8. How do you calculate the oxidation number of an element in a compound? So the oxidation number is the charge an atom has if it was ionized. So we know an atom is oxidized if its oxidation number increases during a reaction. So on the other hand, if the oxidation number of an atom decreases during a reaction, we know that this atom was reduced. Let's see what our junior tutor said. Okay, so the oxidation number is the charge that an atom would have if the compound was composed of ions. They play an important role in the systematic nomenclature of chemical compounds, and it's useful to follow chemical reactions by looking at changes in the oxidation numbers of the atoms in each compound during the reaction. So here they also gave helpful rules to help us determine oxidation number of an atom. So here are the main rules. So we know the oxidation number of an atom is 0 if it's in a neutral substance that contains atoms of only one element. So when you have a gas or a pure liquid, aluminum metal, it's like a solid, they all have an oxidation number of 0. The oxidation number of simple ions is equal to the charge of the ion. So for the sodium ion, it has a +1 charge, so its oxidation number is +1. Similarly, chlorine has a -1 oxidation number. Oxidation number of hydrogen is +1 when it's combined with a nonmetal. So when it's with carbon, nitrogen, or oxygen, it has a +1 oxidation number. But when hydrogen is combined with a metal, so when it's in a hydride, then it has a -1 negative oxidation number. Okay, so they have metals in group 1A have an oxidation number +1. Similarly, elements in group 2A on the periodic table have a +2. And typically, oxygen usually has an oxidation number of -2, but there are some exceptions when it forms a peroxide, then it only has an oxidation number of -1. Elements in group 7A often form compounds so basically fluorine, chlorine, bromine, they all have oxidation numbers of -1. What's also helpful to know is that oxidation numbers in a neutral compound should add up to 0. The sum of the oxidation numbers in a polyatomic ion is equal to the charge on the ion. And also, elements towards the bottom left of the periodic table more likely to have a positive oxidation number than those towards the upper right. So this was a very informative solution. It is also correct. Okay, so now let's check out question number 9. How do you calculate the mole fraction of solute? So I'm going to denote that the mole fraction can be represented by X, and then I'll just put subscript solute. So basically the mole fraction can be defined as the number of moles of solute in a given solution. So let's just write out an expression for this. The molar fraction of solute can be calculated by doing the moles of solute divided by like the total number of moles in the solution. So let's see what our junior tutor said. So one measurement that is used to describe the number of moles of a solute in a given solution is called the mole fraction. Mole fraction of the solute, X, in a given solution can be calculated by dividing the moles of the solute on the total moles of the solution. So the sum of the moles of the solute plus solvent. This can be represented in the equation as moles of solute divided by the moles of solute plus the moles of solvent. Depending on the problem given, you may have to calculate first for the number of moles of the solute and the solvent when only the mass of the said element is given. So here they just have an example where you just need to calculate the number of moles first. So just to simplify it, number of moles is equal to mass over molar mass. So if a question gives you just the masses of the solute and the solvent, then you just need to calculate the number of moles first, and then you can plug it into your mole fraction equation. This solution is correct. Okay, so let's move on to question number 10. What is the lattice energy of some metal halide Mx in the given the following information? So they give us the different enthalpy values for the heat of formation, electron affinity, ionization energy, dissociation energy, and sublimation energy. So it looks pretty intimidating, but I'm going to break down what each of these different values mean. So we're looking for lattice energy, and basically the definition of this is when you have your ions coming together to form your final solid or final like product. So in this example with the metal halide, this is when you have your positive metal plus a negatively charged halide to give our final product. Let's say it's Mx solid. So this is lattice energy. Now let's talk about the heat of formation. So this is the change in enthalpy when 1 mole of a compound is formed from its elements. So in other questions, they might define the heat of formation as kind of like the net, delta H net of the reaction. So for our example, this is the same thing as having our metal as a solid plus our halide as a gas. So these are just the pure elements to make our final product. So this is what I mean by like it's the net of the reaction, because this is basically our final reaction. And all of these little steps are how we would make our final product. Okay, so that's heat of formation, electron affinity. The definition of this is the energy change that occurs when an electron is added. So in our example, this is when you have our halide as a gas plus an electron, and then it ionizes our halide to get X minus. So similarly, you can also have ionization energy. So some people like to see this as like the opposite of electron affinity, because this is the amount of energy needed to remove an electron. From an atom. So in our example, that's when you have our metal as a gas already. An electron is removed, and that's how our metal becomes positively charged. Okay, so moving on, dissociation energy. Dissociation energy. Basically, it's the energy that's needed to break bond. So in our case, let's say we have our elemental halide to come up to break them apart is dissociation energy. Okay, so I'm just going to start a new page to write down the definition of sublimation. So sublimation sounds complicated, but it's actually pretty easy. It's the energy needed to convert solid to gas. So I remember it as they both start with S, like solid and sublimation. And in our case, it's when we have our pure metal solid and we are converting it to a gas. So now that I wrote out all of the different steps, I can make this into a Bourne-Haber cycle. Okay, so again, let's recall that our net reaction is our metal solid coming together with our halide gas to form a metal halide as a solid. The energy that it took to get to that net equation is called the delta H of formation, which was equal to negative 500 kilojoules. So that's why I had an arrow going down. So in order to get from our elemental solids and gases, we first need to convert our solids to gas, and then our gas needs to be ionized. So I'm going to write it out like this. So I'm going to do an up arrow to show that we need energy. I'm going to show that our metal solid needs to first be converted to the gas. So this is called sublimation. And this had a value of positive 550 kilojoules. So now that we have our metal as a gas, I want to convert my halide to a gas, but I first need to, well, it is a gas. I first need to break apart the X2 bond. So I'm going to write out that the bond dissociation needs to occur just to get a halide on its own. And this required 300 kilojoules of energy. And then what also requires energy is ionizing our metal to make it positively charged. So we have now our metal as a gas, and then it will be ionized to M plus an electron. So this is ionization energy, and it has a value of 700 kilojoules. So those are all of our positive values. I'm going to draw the other half of our Bourne-Haber cycle. So going down, what released energy was our halide gaining an electron to become negatively charged species. So this released 400 kilojoules. And what also released energy is the value that we're looking for, called lattice energy. So again, just to refresh, this is when we have our ionized metal, our ionized halide coming together to form the final product, MX solid. So here you can see that our cycle is now complete. We took our raw elements, converted the solid to gas, and then ionize the gases. And then once we have the ions, they come together to form our final product. So this can be written as an equation where you have your delta H of formation is equal to the sum of all these different energy steps. So again, delta H of formation is equal to delta H sublimation, dissociation, ionization energy, which can occur in more than one steps. Same with electron affinity, it can occur in multiple steps. And finally, lattice energy. So now I can rearrange this equation to solve for lattice energy, which is what the question is looking for. So I'm just going to move all of these values to the left, so they all just become negative. Okay, so now I'm going to plug in all these values. Delta H of formation was negative 500. Delta H of sublimation was 550. Delta H of dissociation was 300. Ionization energy was 700. And then the electron affinity was minus 400. So if we add all these values together, you get minus 1,650 kilojoules as our delta H. So you also know you did it right because the delta H, your lattice energy, is typically always negative. Since the ions coming together is favorable. So this is the same thing. It's 1,650 is option C. Oh, 3, sorry. Option 3. So let's see what our junior tutor said. Third option. Explanation is lattice energy is an estimate of the bond strength in ionic compounds. It is defined as the heat of formation of ions of opposite charge in the gas phase to combine into an ionic solid. It is used to explain the stability of ionic solids. To calculate the lattice energy of an ionic solid, Bourne-Haber cycles can be applied, and the concept of ionization energy, electron affinity, dissociation energy, sublimation, the heat of formation, and Hess's law should be understood first. So this is why I also wrote down all the definitions. Ionization energy is the energy required to remove an electron. Electron affinity is the energy released when an electron is added. Dissociation energy is the energy required to break apart a compound. Sublimation energy is the energy required to case a change. I guess it's required to change the phase from solid to gas, bypassing the liquid phase. Heat of formation is the change in energy when forming a compound from its elements. And then Hess's law states that the overall change in energy of a process can be determined by breaking down into steps. then adding the changes in energy of each step. So that's what we did in the last part here. So the Bourne-Haber cycle is essentially Hess's law applied to an ionic solid. The Bourne-Haber cycle can be reduced to a single equation where heat of formation is equal to heat of atomization. So this is the same thing as the lattice energy. Oh, I know. It's the same thing as when you atomize one of the gases, I believe. Dissociation energy, so that's breaking apart the halide, plus the sum of ionization energies, plus the sum of electron affinities, plus lattice energy. Oh, okay, so heat of atomization is the same thing as sublimation. So then they also rearranged the formula for lattice energy. So they did lattice energy is equal to heat of formation minus sublimation minus dissociation minus the sum of ionization energies minus the sum of electron affinities. And then they also got minus 1,650 kilojoules. I'm just going to say this solution is correct. So I think that's all the time we have for today. So if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you liked today's video, go ahead and give it a like and also leave a comment. And you can also share this video with all your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.